Hi there, welcome to the 31st episode of the Synth project, where we are going to build a synth together. Today we will continue the design and testing of the CV processor, adding a new component to it, the Limitator, which can establish an upper boundary to the control voltage at its input, preventing it to exceed such boundary. Let's begin. As you may remember from a previous episode, the Limitator has a very simple block diagram. It is a device that has just one input, one output and a potentiometer to set the upper boundary of the control voltage. With this device we can define the upper value of a control voltage being used to control one or more modules of the synth. This is useful in several cases, for example, when we generate a control voltage with a soft pot to control the VCO, and we don't want that the frequency goes above a certain value. Let's take a look at the schematic to see how we can implement such a circuit. The trick for designing such a circuit is to use a DC amplifier with a gain less or equal to 1, and let the control voltage go through it. When the gain is exactly 1, the output signal will be identical to the input, and we will have no limitation. When the gain is 0, there is not going to be any output signal, and the limitation is at its max. Anywhere in between these two extremes, we will have an output signal that is lower than the input signal. This behavior will allow us to have an output signal that has the exact same shape as the input signal, but with a smaller amplitude than the original input signal. To make the amplifier, I decided to use an op-amp. However, I couldn't use a non-inverting amplifier because it would give me a gain that is always greater than 1. So I had to use an inverting amplifier configuration, set for it a gain between -1 and 0, let the input signal go through it, and then let the signal go through another inverting amplifier with a gain of -1, so that the final output is positive again. The first amplifier is done with the first half of the LM358. The input signal enters through the pin header P9 and goes through resistor R12, which is one of the two resistors that set the gain for the amplifier. Resistor R18 is only used to keep the op-amp input to ground if there is no signal present at the input. The second resistor that sets the gain of the amplifier is the potentiometer RP6, which has the same value as resistor R12. This way, when the potentiometer is set at the max resistance value, the gain will be -1, and when the potentiometer is set at the value 0 of resistance, the gain is 0. The second half of the LM358 is used to make the second inverting amplifier with a gain of -1, which is achieved using two identical resistors for R14 and R15. The gain of the two stages will be the product of the two independent gains, and so it will go between 0 and +1. The two capacitors C9 and C10 are used to prevent oscillations at high frequencies by creating a negative feedback that cancels them entirely. To use this circuit, we just need to input a signal, set the desired limiting factor with the potentiometer, and extract the output at pin 7 of the LM358. Let's now test this circuit in the lab to verify that it works as expected. So, this is the same breadboard that we used the last time to test the DC mixer, which is located in this area. I have added the limitator circuit on the same board, right here above the DC mixer. This is the LM358, which provides the two op-amps necessary for this circuit, and is surrounded by the rest of the circuitry as described in the schematic we just examined. I am using again my function generator to emulate a control voltage to put at the input of the circuit. Right now, the generator is set to create a square wave at a frequency of 100 Hz and an amplitude of going from 0 volts to +10 volts. Here on the oscilloscope we can see the same signal in blue and the output of the limitator in yellow. The output of the limitator is extracted here on the breadboard directly from pin 7 of the LM358. With this setup we have a sort of control voltage that changes over time from 0 volts to plus 10 volts at a frequency of 100 Hz, as visible on the blue trace on the oscilloscope. And actually, to make things closer to reality, I'm going to change the frequency of the input signal to 10 Hz, much closer to what a real control voltage would do. And now let's adjust the x-axis scale of the oscilloscope so we can have a better view of how the signal changes, both in input and in output. So how does the limitator work? Well, moving the potentiometer that sets the upper limit, we should see the upper part of the output signal change. Let's do that and see if it actually happens. And yes, here is the limitation pushed to the max, and therefore the signal is totally disappeared. And here instead is the minimum amount of limitation, where the whole signal basically passes through the output. To show how the output signal would look like if we had an input signal changing slowly, let's change the shape of the input wave to a triangular wave. Now the input wave goes from 0 volts to 10 volts linearly, and then back to 0 volts in the same way. And as you can see, the output wave reflects exactly the same shape. But if we move the potentiometer to increase the limitation, the upper value of the output will start decreasing, while keeping exactly the same shape of the input, which tells us that the limitation is applied linearly to the whole input signal. In other words, the output signal is a scaled-down version of the input signal, so that such output signal will not exceed the level imposed by the limitator. Let's now take a look at how the limitator works along with the DC mixer. In particular, we can see the behavior of the signal once we cascade the two circuits together. To do so, we need to move the output of the signal generator from the limitator input to one of the DC mixer's inputs, in this case input 1. The output of the DC mixer will go instead to the input of the limitator. The oscilloscope will still be connected to the limitator output. Let's use once again the 10 Hz square wave. And here in yellow is the output, where the DC mixer offset is set to 0 and the limitator is set to its maximum limitation. Now I am moving the limitator potentiometer to reduce the limitation, until it is totally eliminated. And you can see that now the output is mimicking exactly the input from the function generator. Let's now add some offset. And the minimum value of the output is now increasing. Actually, it is the whole output that is increasing, but since we have a square wave that has already the maximum possible level, the upper part of the output is not changing. While changing the value of the offset, we can also change the limitation value. This way, the signal is forced to stay between the minimum value forced by the offset and the maximum value forced by the limitator. This way, we can create a new control voltage that goes between a minimum and a maximum value imposed by the controls of our circuitry. Let me show now another interesting thing, the possibility of creating distortions of the control voltage when forcing the DC mixer into saturation, which can be done by applying an offset to the DC mixer while leaving the input voltage to the max value possible. So let's start by removing the offset and increasing the limitation to the max. Now let me change the input signal from a square wave to a triangular wave again, otherwise we will not be able to see the distortion. Now, removing the limitation, the output signal shows the same triangular shape. But now, if we increase the offset, keeping the DC mixer input controller to the max, we should be able to push the mixer into saturation. Let's see if it works. And yes, you can see how the top of the output signal starts flattening when I increase enough the offset. And of course, I can keep adjusting the controls to increase and decrease the distortion at will. And that's all for today. At this point, we already have 2 of the 5 circuits that compose the CD processor. In the next video of the series, we will talk about the sample and hold component, and we will see how we can have it interact with the other circuits of the processor. To avoid missing the next episodes, please remember to subscribe to the channel if you haven't done so already, and also make sure you have your notifications enabled. See you soon in the next video, and as usual, happy experiments!